All right, we've developed this idea that we call Euler's Second Law, which says that the time derivative of the angular momentum about the center of mass, as observed in the inertial reference frame, is equal to the total moment due to the external forces about the center of mass. Now, just like all of the other expressions that we have, we need to parameterize each of these parts and then solve for, in this case, the equations of motion and the constraint equations to have something useful. So on the right-hand side, we have the moment about the center of mass. We calculate that using r cross f, where the position vector is going from the center of mass to the location of each of the forces. And on the left-hand side, we have our time derivative observed in the inertial reference frame, which we're comfortable with by now. And we recognize the angular momentum about the center of mass. And we've calculated this for a series of particles, but we need to develop how we use this expression when dealing with a continuous rigid body. So to do that, we'll begin with our expression for our series of particles, which we said is the summation of the mass multiplied times the cross product of the position vector to each of the particles with the velocity as observed in the inertial reference frame of each individual particle. So first we'll rewrite the inertial velocity with respect to the center of mass in terms of an observation made on the body. So if we observe the inertial velocity with respect to center mass on the body, then we need to transport this using our omega of the body frame with respect to the inertial reference frame in this expression. Now when we make the observation on the body of the velocity of each of the particles, this is equal to 0. And so we'll substitute this expression into the velocity as observed in the inertial reference frame. And this gives us the relationship between the angular velocity of the rigid body observed in the inertial reference frame and the position vector in the context of the angular momentum. And I should point out here that we're going to do this entire derivation by keeping the multi-particle system definition instead of using the continuous body, and we'll convert it to a continuous body at the very end. But now that we've incorporated the angular velocity, this is equal to omega b in the b3 direction. And so here we've put our first constraint on this system and made it specific to planar motion because we're saying that the angular velocity itself is only acting in the b3 direction or out of the page. And so after making this insertion, we can move our scalars outside of the cross product. So we'll remove our omega b as well as our mi out of this cross product expression. And so now let's examine the direction of this expression, r cross the quantity b3 cross r. And so if we draw our vectors, here's our b3 director pointing out of the page, and then we have a position vector, r of I with respect to g, and that's always in the plane. And so if we cross our position vector with b3, we're going to obtain a vector that's orthogonal in this direction. Because it's a cross product, it's always 90 degrees to both of these vectors, it's orthogonal, and then we're going to cross r with our new vector, and when we do this, we obtain a vector pointing right back at us, so it's in the b3 direction. So we see here that this vector, r cross b cross r, is always going to be in the e3 direction, and then the sign of the scalar, the mass multiplied times the angular velocity, is going to give us whether it's in the positive b3 or negative b3 direction. So let's write our angular momentum about the center of mass in terms of a dot product, where we say that the scalar, h sub g, is equal to the angular momentum as observed in the inertial reference frame, dotted in the b3 direction, and we'll take this entire expression and dot it with b3. And so next we'll use two vector identities. The first is that we can switch the order of this cross product, and as long as we switch the order of this cross product, we'll have the same thing. And so this vector identity will give us the following expression, in which we're still calculating the scalar of the angular momentum with this expression, but it now has r cross b, and then it's that quantity crossed with the position vector r. And now we can apply our next vector identity, which says that a cross b quantity dotted with c is equal to a dotted with b cross c. And so in this case, our a term is equal to our position vector crossed with b3, B is equal to the position vector, and then C we set equal to B3. And so you can see that corresponds with the first part of this expression, the second part of this expression, and then the dot product with B3. And so substituting these in, we can now rewrite the expression into a much more convenient form. And this shows us that we have the dot product of two expressions that are the same with each other. And so now we can collapse this into an expression in which we have the magnitude of our angular momentum is equal to the angular speed, keep our summation of our particles, and then this will be the mass of each particle multiplied times the norm of the position vector, I with respect to g, squared. And this is coming from the fact that we have the magnitudes of these two expressions that are squared and the magnitude of our unit vectors, which are 1. And it's simply a magnitude, so it's the norm of this vector squared. And so we see that in summary, we now have a new quantity that's a scalar. And so now we see that our angular momentum is a scalar that's in the B3 direction that's created by the angular velocity multiplied by this new scalar, which is the mass-weighted position of each of the particles with respect to the center of mass. And so we call this the moment of inertia, or I sub g. And so we have the formal definition here, which is the moment of inertia of a planar body about the center of mass. G is the sum of the mass-weighted squared distances of each of the points relative to the center of mass. And so for a continuous body, we now make this an integral across the body, and it's integral across the differential masses, which we've already expressed as a density multiplied times the differential volume. And now in vector form, we see that the angular momentum about the center of mass, as observed in the inertial reference frame, is equal to the moment of inertia about the center of mass, which is a scalar in planar motion, multiplied by the angular velocity of the body frame itself, as observed in the inertial reference frame. Now, another thing that we need to consider here is that this expression doesn't hold true for 3 dimensions. So we've restricted to planar motion, and 3 dimensions is an entirely different ball of wax, which we need to deal with tensors, and here we're only dealing with a single scalar that would come from that tensor. So now we've identified how to quantify the angular momentum of a rigid body. And when we insert this into Euler's second law, we now have an expression where we're taking the time derivative of the angular momentum, and when we do this, we have the time derivative, as observed in the inertial reference frame, of the scalar mass moment of inertia about the center of mass multiplied times omega, b as observed in I. And when we do this, we'll get the expression I alpha, b as observed in I, and that's an angular acceleration vector. And so now Euler's second law about the center of mass and planar motion ends up being the expression the moment of inertia multiplied times the angular acceleration vector is equal to the moments caused by all the forces about the center of mass. We need to switch these to the notation we're using, where the alpha of b, as observed in the inertial reference frame, is equal to the scalar, which is the angular acceleration of the body, so that if you make it theta, it would be theta dot, theta double dot. In this case, we have omega sub b, and so this is the time derivative of omega sub b in the B3 direction. And you can see here that this is an equation of motion because we've now linked alpha, which is a second order term, with our moment. So we have a second order differential equation. This is our rotational equation of motion. We can combine this with Euler's first law, which gives us 2 translational equations, which are second order equations, and be able to calculate all of our constraints and equations of motion for each of our degrees of freedom.